All right, so in the previous section, we learned how to graph linear inequalities. And so we did something like this. We graphed this first one. Our intercept is at -2. And then we rise 1, run 1, and so on. And that's going to be a dashed line. Okay. And if I plug in 0, I get 0 is greater than -2. That's true. So this one is shaded this way. Okay. And then down here, I have my intercept at +1, and my slope is -1. So I'm going to rise and run the other way, and that is a solid line. And 0 is less than or equal to 1. That's true. So it's going to get shaded down here. So now what we want to do in this section is we want to solve systems of linear inequalities. And so in other words, we want to know where this inequality and this inequality intersect. Okay, where these two graphs would intersect. And so what we do is we put them on the same coordinate plane. So the first one was y is greater than x minus 2. So we started at 2. Let me get that centered for you, sorry. We rose 1, ran 1, rose 1, ran 1, and we put a dotted line. Okay, and we shaded this way. I'm just going to real lightly shade that way. Okay, very non-straight line. And then our other equation was y is less than or equal to minus x plus 1. So we started here at +1. The slope was negative, so we rose 1, ran -1. And we could do that again. And this one is a solid line. And 0 is less than 1, so we shaded this one this way. Okay, so what our answer is where the two shadings overlap, which is all of this. So the region that's described by those inequalities is this region. This solid line, this dotted line, and everything between them as such. That would be the answer. So really, not doing anything tremendously different. Just adding another step to the problem. So let's see. Here we have y is less than 2x. So again, we graph that. It's in slope-intercept form. So the intercept, when it's not out here, is 0. So this goes through the origin. So start at 0, and then the slope for that top line is 2. So I'm going to rise 2 and run 1. Rise 2 and run 1. And that is a dotted line. Okay. And then I can't plug in the origin to see whether or not where to shade. So what I do is I pick another point. So I'm going to pick the point 3, 1. So I'm going to plug in 3 for x and 1 for y. So I have the equation y is less than 2x. I'm going to plug in the point 3, 1. So 1 is less than 2 times 3 is 6. That's true. So this one is going to get shaded this way. And again, I'm just going to make some real light markings there. Okay. This other line doesn't have an X with it. So if you recall, Y equals lines are either horizontal or vertical. The ones that have Y only are horizontal. So this is the horizontal line through 3 on the Y axis. So here's 3 on the Y axis. It too is going to be a dotted line. Okay. And greater than, we really don't need to plug in a point. Any numbers up here are greater than. These are the greater thans. These are the less thans. Okay. So anything from here up is greater than. Anything from here down is less than. So this gets shaded this way. So where do my two shadings overlap? They overlap in this little triangle up here. And that's my answer. I guess it's a trapezoid, not a triangle. The one on the other page was a little triangle. The trapezoid. Okay. There we go. That's my answer. Okay. Last one. No, two more, I guess. So one more after this one. So again, slope-intercept form. The intercept is 1. So I start there. And I'm going to rise -2 and run +1 because this has a negative slope. It is a solid line. If I plug in the origin, I get 0 is greater than or equal to 1. And that's not true. So this gets shaded this way. Okay, away from the origin. And then this other one, the y-intercept is at 2. So that's there. And the slope is 1, +1. And this would be a dotted line because it's strictly greater than. And if I plug in the origin, I get 0 is greater than 2. That's also not true. So it's getting shaded this way. And where do my shadings overlap? Right up in here. This time it is a triangle. Okay, like triangles. In engineering, triangles are some of the strongest supports. That's why you see a lot of bridges. If you look at a bridge sideways in the infrastructure, there's a lot of triangles in some bridges. I think they've added more modern approaches nowadays. The older bridges, at least. So anyway, there's my answer. And last example. So we have the first line, the intercept is at 2. So here, the slope is -1. So down 1/1. It's a dotted line. Dot it. Dot it. The other one, the intercept is at -2. The slope is the same. Down 1/1. It's negative. It too is a dotted line. Okay. Now, if this were solving a system of linear equalities, linear equations, we would say there's no solution. The lines are parallel. But let's see. 0 is greater than 2. Is that true? No. So this line is actually getting shaded this way. And 0 is less than -2. That's not true either. This line's getting shaded this way. Where do the shadings overlap? They don't. So it is no solution. But had this one been less than, and I would have shaded this way, and this one been greater than, and I would have shaded this way, then the answer would be the lines, the shaded area bounded by those lines. The lines would not be included. But as it is, it's shaded the other way, so no solution. They don't have anything in common. that is it for section 5.